Hello everyone, now we will discuss on the topic tertiary treatment part 1. So, in our previous classes we have seen that wastewater treatment contains different steps and the last step is tertiary treatment which starts after secondary treatment, and in this step the main objective is to remove the residual BOD, COD and TDS and microorganisms. So, pathogens are also killed in this step, and we will discuss here on this topic that adsorptive filtration, then membrane processes and advanced oxidation processes. So, as we have already mentioned that tertiary treatment is the final stage of multi-stage wastewater cleaning process, and it removes inorganic compound, bacteria, viruses and parasites and makes the treated water safe to reuse, recycle or release into the environment. After this treatment step, we can consume the treated water for different applications. We have already discussed that in normal practice the TDS and BOD are mostly removed in primary and secondary treatment steps, but some residual amount may be available, and in this case the water is filtered through different beds or some membrane unit is used or some advanced oxidation processes can also be applied, and it is possible that in the secondary treatment some BOD is still remaining and some coagulation is also required apart from this adsorption and membrane process or any advanced oxidation process. So, alum also causes any solids that were not removed by primary and secondary wastewater treatment to group. So, they can be removed by filters, and as you have mentioned that the disinfection or killing of the microorganisms, particularly the pathogens present in the water, treated water is very essential, and disinfection step where chlorine is added is also included in the tertiary treatment step. But we also discussed that if the chlorine dose is not maintained, then the residual chlorine will be available. Thus, to remove that chlorine, some chemicals like sodium bisulfite is added in the treated water. So, important tertiary treatment processes are adsorption, reverse osmosis and advanced oxidation. Now, we will discuss adsorptive filtration process. So, as shown here in this filter unit, we see the wastewater is coming here, that is after secondary treatment, and then it is going through this bed where coarse media, then fine media, then finest media and then support media, then treated effluent is coming out, and during backwash we send water in reverse direction and we get the backwash. So, in this case activated carbon is mostly used here, as shown here it is a coal, but activated carbon is mostly used, and adsorption is the process which takes place here for the separation of the pollutants from this wastewater, and this adsorption is a surface process, is a surface phenomena where the pollutants are adsorbed on the surface of these adsorbents or different beds as mentioned here. So, this absorption can take place by physical or chemical route, and this slide gives us some information on the mechanism of the adsorption of the pollutants on the surface. So, the first step is transport of adsorbent from bulk to the surface of adsorbent. So, from the bulk of the solution the adsorbent comes on the surface of the adsorbent, and then second step is diffusion of adsorbent into the interior part of the adsorbent. So, pollutants or adsorbents gets entry into the interior part of it and physically trapped. So, this is physical adsorption. Then the third step is adsorptions of adsorbate by following possible routes, that is physical adsorption or maybe some chemical adsorption. Then that means the adsorbents or pollutants are coming in the surface of this adsorbent, where the surface is having some active sites as shown here, say positively charged active sites, and if our adsorbent is negatively charged. So, then they will be chemically attracted and will be attached like this. So, this is chemical adsorptions or chemisorption. Similarly, negatively charged surface and positively charged ions can also be chemically adsorbed. Apart from that, ion exchange mechanism can also take place here, like for example, say if we have ferrous oxide and ferrous hydroxide impregnated activated carbon surface. So, this is presented here. If in the solution arsenic is present, that is in this form, that is negatively charged. So, this OH minus ion can be replaced by this arsenite or arsenate ions. So, like this, the surface will be converted into this form. So, this OH is replaced by this one. So, that is called OH, that is hydroxyl ion exchange. So, these are the different mechanisms through which the adsorption can take place. Now, there are many factors which influence the performance of the adsorption process, like say temperature and concentration of pollutants or adsorbents, then contact time of adsorbate and adsorbent. That is why we need to provide sufficient residence time of the water in the adsorbent bed, and then adsorbent dose. So, what is the dose? Particularly we will see that this process may be of batch or continuous operation. In case of batch study, we will be talking about the adsorbent dose per unit volume of the solution, or in case of continuous study, we will be talking about the amount of adsorbed used in the column. And then pH of the solution, pH of the solution plays an important role, because the adsorption phenomena is influenced by the solution phase chemistry of the adsorbent and the adsorbate, as well as the surface charge of the adsorbent, which changes with pH. So, this is very important parameter out of all those parameters in terms of adsorption capacity or adsorption performance. And zero charge potential of the adsorbent helps to understand the effect of pH on the adsorbent process. So, zero charge potentials means there is some pH at which the surface charge becomes neutral or zero charge. So, above that pH the surface of the adsorbent is negatively charged, and below that pH the surface is positively charged. So, if solution in the solution negatively charged ion is present, so that will be preferably adsorbed when the pH is lower than the pH ZPC, and when in the solution positively charged ions are present, those will be preferably adsorbed on the adsorbent surface when pH ZPC value is more than the solution pH. Now, we will show some example how to improve the performance efficiency of adsorbent by surface modification. As you have discussed that positively charged sites will attract negatively charged ions in the from the solution. So, if in the solution you have negatively charged ion and surface adsorbent surface has some positive charge density, if we can increase the positive charge density, then it will attract more negatively charged ion, or more effectively it will attract negatively charged ion. So, for example, say GAC, granular activated carbon, if we see in the GAC both positive and negative active sites are available as shown here, positive negative positive 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 negative positive negative, like this surface charge is there. But due to the presence of this type of activities active sites, it is not very effective for the removal of the negatively charged ions like arsenic. So, if we impregnate or if we modify the surface by some positively charged ions like say Ca2 plus. So, this one Ca2 plus one ion will neutralize this negatively charged and it will create one positive charge. So, here also another Ca2 plus is coming in contact with this negatively sites, and then it is giving another positively charged. So, at the initial stage we have here 2 del positive. So, you see 1 2 3 4 5 minus 3 negative. So, then plus 2 del your net positive charge, but after surface modifications we are getting plus 6 del plus 6 positive charge. Another calcium 2 plus impregnation is resulting 8 plus 8 del plus NPC net positive charge. So, by the impregnation of metals we are able to increase the positive charge density in the surface of the adsorbent. As a result, its capacity to capture the negatively charged ions from the solution will increase, and as a result at neutral pH arsenic removal efficiency of GSE is very less due to its predominantly negatively charged surface. In our experiment, that is 16 gram per liter adsorbent dose and 24-hour agitation, the arsenic concentration in the treated water would not be reduced from 188 ppb to 50 ppb. So, this is our own study. So, but when it was impregnated with calcium 2 plus ion, so this arsenic removal was much more better than this. And then how can we evaluate the performance? Performance means, say if we are asked to design a adsorption column or any filter unit for the treatment of wastewater. So, we have to decide its size, we have to decide the amount of adsorbent required. So, one is adsorption capacity, that is specific uptake. So, that is mg per gram or kg that unit, that is adsorbate mass of adsorbate captured on unit mass of the adsorbent. So, that way we can evaluate the performance of the adsorbents. And adsorption kinetics, what is the rate of the adsorptions. So, what will be the retention time we have to provide during its attachment or during the removal of the pollutants from the wastewater. So, that adsorption kinetics is also important, and after that the spent adsorbent management or regeneration, what we will do with the spent adsorbent, that is also an issue. So, all those information we should have, and we should have good knowledge on that, so that we can understand the phenomena and we can design a system for the effective treatment of wastewater. So, specific uptake is determined through its isotherm study, and important isotherm models are Langmuir isotherm. So, Langmuir isotherm, this it assumes a monolayer adsorptions on a uniform adsorbent surface with energetically identical sorption sites, and this is the formula. So, Q equal to Q BLC by 1 plus BLC, where C is the equilibrium concentration of the pollutant and Q is the specific uptake at equilibrium, Q is the maximum adsorption capacity or maximum specific uptake, and BL is the Langmuir constant, which gives some idea about the rate of adsorption. So, this is Langmuir isotherm, and mostly it is used to calculate the maximum adsorption capacity of the adsorbent for that particular pollutant within certain range of initial concentration of that pollutant or adsorbate. Similarly, another mostly used isotherm is your Freundlich isotherm. Before that, we will discuss on the suitability of use of Langmuir isotherm. So, here we see that the feasibility of Langmuir isotherm can be described by a separation factor RL, which can be determined by following equation: RL is equal to 1 by 1 plus BL into CO. So, now if RL value is greater than 1, that means adsorption process unfavorable. If RL equal to 1, then it is linear, and it is 0 less than RL less than 1, then it is favorable and irreversible when RL is equal to 0. So, this RL value if we determine from the experiment, then we can get some idea whether the adsorptions will be favorable or not. And then another adsorption isotherm which is mostly used, that is Freundlich isotherm, and Freundlich adsorption isotherm describes equilibrium on heterogeneous surfaces and hence does not assume monolayer capacity. The logarithmic form of the Freundlich isotherm expressions is given in this expression, that is ln Q equal to ln K plus 1 by n ln Ce. So, by doing experiment we can find out the value of Kf and n. So, these Kf and n are Freundlich constant, and this can be determined from the experiment. and these can be used to get some idea whether the adsorption process is following these routes or these phenomena or not. Okay. So, this is for single component adsorption, but if there are multiple pollutants and multiple adsorbate, then multi component systems, for that multi component systems modified competitive Langmuir model, extended Langmuir model and extended Freundlich model are used. Adsorption kinetics, different models are used, that is pseudo first order model, pseudo second order model and Weber and Morris model, that is intraparticle diffusion models are used. So, the pseudo first order model expressions is like this. So, here K 1 is the rate constant and then Q E equilibrium specific uptake and Q T specific uptake at any time. So, this is the, and for the second order pseudo second order kinetic model, the expression is like this. So, in both the expressions we have one rate constant, another is Q E value we can calculate. So, from this we can calculate the Q E value and theoretically how much Q E equilibrium constant specific uptake, equilibrium specific uptake we are calculating experimentally, and which we are getting from this, that will give us some error, and the error value will help us to determine which method is more accurately representing the phenomena. And Weber and Morris model, this model is, this is the expression of this model and this is used to give more interpretation on the interparticle diffusion. And here K, I, D and C, these two are the constants and the rate constant K, I, D for interparticle diffusion, and C is a constant that gives an idea about the thickness of the boundary layer. The larger the value of the C, the greater is the boundary layer effect. So, this model is very useful to investigate the pore diffusion in adsorption, that is interparticle diffusion, and to understand the implication of data for improved adsorbent and process design. Then spent adsorbent generation. So, after the adsorption process, the all pollutants or adsorbates are adsorbed on the surface of the adsorbent. So, depending upon the toxicity of the adsorbate or the pollutants, the adsorbents will also be toxic. So, we need to handle it very carefully. So, we can regenerate it. So, we can dissolve the adsorbed pollutants or adsorbate, but in that case again we are creating some toxic substances, management of that is also very essential. Or we can use this spent adsorbent for solidification purpose, so that that will be solidified with concrete. So, that will not come into the environment, or we can use it for landfilling, or we can manage it as per the hazardous waste management procedure. Now, we will see the adsorption types and reactors used. So, as shown here, there are one batch type of operation and continuous type of operation we are seeing here. So, this is a slurry reactor, that we can say in a batch liquid is coming and then powdered adsorbent is put, and then we are providing some agitation and mixing and a slurry is formed, and pollutants present in the water, bulk of the solution comes on the surface of it and gets adsorbed. So, after certain time interval we get the removal of the pollutants from the water. So, with increasing of agitation time, the concentration of the pollutants in the solution gradually decreases, and after certain time it becomes free from the pollutants. And here we see the continuous operation, we are sending the feed from the top and from the bottom we are getting the treated water, and this is our adsorption bed, this is a fixed bed, and after certain time of operation this fixed bed will be exhausted, that means will be the adsorbent will be converted to spent adsorbent, and at that time the concentration of the pollutants present in the feed and in the treated water will be same. So, that will not be working. So, we need desorption. So, at that time we have to give wash water or some other methods we can apply for the desorptions of the adsorbed pollutants from it, and then this bed will be free and can be used further. So, that in a cycle one bed is in operation and other bed is in regeneration can be possible. Here we have seen that from the top the feed is coming, on the vice versa the feed may come from the bottom and it can be treated water can go from the top also. Different configurations can be used, as already we have discussed in previous classes. So, this is the continuous operation and this is our batch operation, and for the application point of view we go for continuous operation, and for basic understanding of the process, whether the particular pollutant will be removed by a particular type of adsorbent or not, what will be the residence time requirement and what will be the specific capacity. So, all those things we can determine in the batch scale. Now, we will discuss how we will understand the phenomena which is going on in a fixed bed adsorption column, or how can we model this, okay, how can we determine different parameters during the adsorptions in the packed bed, so or fixed bed. So, that we will be discussing. Now, you see we have to make some assumptions to simplify the phenomena for the initial understanding. So, those assumptions are internal and external mass transfer resistances are very small. When the water is flowing in this bed, so then we are assuming that there is no internal and external mass transfer resistances. That is very simple assumption, but this will never happen in reality, and plug flow is achieved. We are assuming that the flow is following a plug flow through this bed, that means axial dispersion is negligible. The concentration across this diameter is always constant, and then the adsorbents is initially free from the adsorbate. Initially this adsorbent is not having any adsorbent, the adsorbate is only available in the feed. Adsorbate means pollutant here. So, pollutant is present in feed, but there is no pollutant in the adsorbent at the initial stage, and adsorption isotherm initially begins at the origin. So, at the very starting point the pollutants are being captured by the adsorbent. So, with more run time, so next layers are getting are capturing the pollutants. That means, with time the exhausted bed size is increasing. Okay. So, this is one typical example, say for this is length, up to this length this bed is exhausted first, then this bed will be exhausted. That means, here the pollutants are captured by the adsorbent, and here the pollutants are not captured by the adsorbent, because pollutants are not available, all pollutants have been captured in this adsorbent. So, these are our assumptions basically. Adsorption isotherm initially begins at the origin, then local equilibrium between the fluid and adsorbent is achieved instantaneously. Okay. And then in that case which we see, in the whole bed some part will be exhausted, some part of the adsorbent will not be exhausted at all, it will be free for the adsorption. So, this is our stoichiometric front. So, this line is our stoichiometric front. What does it mean? By stoichiometry or by mass balance we can calculate what is the length of the this part where the pollutants have been captured. That means, total pollutants present in this feed that will be available in the zone. That means, that pollutants, that amount of pollutants is being captured by the material present in this zone. So, we can represent like this. So, solute concentration at the very 0 stage with respect to this position. So, here the solute concentration is the feed concentration maximum, then this is L, after that solute concentration is 0. So, this in the water there is no solute. So, this is, so this part is our LUB and the material present in is, that is WUB. So, LUB and WUB length and weight of the bed section downstream of the front, this front stoichiometric front, and LES and WS the length and weight of the bed section upstream of the front. So, this is provided here. So, this is our stoichiometric front. Now, this is as per our assumption, then the main assumption is that there is no mass transfer resistance and plug flow situation prevails in the bed. So, in this case what we will see, after a certain time called the stoichiometric time, the stoichiometric wave front reaches the end of the bed. So, if it is the bed which we had, this was front, certain time this front will reach here. Okay. The concentration of the solute in the fluid abruptly rises to the inlet value Cf, no further adsorption is possible and the adsorption step is terminated. This point is referred to as the break point and the stoichiometric wave front becomes the ideal breakthrough curve. So, this is the ideal breakthrough curve, it gives, that is ideal breakthrough curve. Okay. And if any length that we are talking about which is less than the LB. So, this is our LB and this is our L, any length less than the LB we can calculate the value of L by mass balance, that is equal to LES. Okay. So, how we can do it, that is by mass balance, solute in entering feed and that is equal to adsorbate captured by the material in the L ideal. So, that is what is that, QF flow rate into T ideal, that is equal to volume of inlet into Cf, the concentration of the pollutant in the inlet. So, total solute in the entering in the feed and adsorbate. So, this is our total bed length LB, we have front here L ideal, because we are assuming that this front is moving under ideal condition. The real assumptions, the assumptions are ideal. So, this is ideal front and in that case this L is ideal. So, L ideal divided by LB, if this is the S is the material present in the whole length. So, within L ideal how much material is present, S into L ideal divided by LB. So, this S into L ideal divided by LB. So, this is the material present in it here. So, this material into QF, that is the specific uptake, that will be the adsorbate which is captured by this part, the adsorbent present in this part. So, these are the same. So, this by equating these two we can calculate the value of L ideal. Okay, we can get the value of L ideal and L ideal is nothing but LES. So, LES we can calculate now QF CF T ideal by QF S into LB. So, just we have discussed in the previous slide. So, then how we can get the LUB? LUB is equal to LB minus LES, because this is our LB whole and this is our LES and LUB this one. So, total is LB. So, LB equal to LUB plus LES or LUB equal to LB minus LES. So, that we can, once the LB is known, LES is calculated by this, we can calculate the value of LUB. So, this is possible for ideal condition, but in nature this will not happen. Okay. In a real fixed bed adsorber, the above assumptions are not valid. Internal transport resistance and in some cases external transport resistance are finite and axial dispersion can also be significant, particularly at low flow rates in shallow beds. So, here say if we have a bed here and with respect to time we are measuring the concentration here. So, different length. So, we are taking sample here. So, at t equal to 0 we are taking sample. So, at t equal to 0 in all the cases the concentration of the pollutants will be 0, but when we will be increasing the time, so after say half an hour or 20 minutes or 10 minutes, after 10 minutes, 15 minutes, 20 minutes, if we carry out the experiment, then we will see that the concentration here will be increasing gradually, still here the concentration will be 0, further we can go ahead and the same trend we will get. So, you see with respect to length, if we see the C by Cf value, that is the C is the concentration of pollutants in the outlet and Cf is the concentration of pollutant in the inlet. So, that value with respect to that will be changing like this with length for a constant time. Let us say for T1 we are taking this one, but for T2 this will be like this, and for Tb this will be like this. So, if we take one case for a time t2, then this graph this curve if we consider. So, here this is Ls and Lf. So, this Lf is showing that most of the material when L less than Ls. Okay. So, this Ls and Lf. Now, if L is less than Ls for t equal to T2, that means this part, then we can say that the bed is almost saturated, because C by Cf is almost near to 1 up to this, then it is gradually decreasing, and here at Lf when L is greater than Lf, that means this side, this part is not used at all, unused bed. Okay. So, almost clean bed, but in between Ls and Lf then there is some mass transfer. So, this is mass transfer zone, this part. Okay. And if we represent this C by Cf with respect to time for the whole this Lb, then that will be changing like this. Okay. With respect to time, the S shaped curve we will get, that is called breakthrough curve, and Lf can be taken where C by Cf equal to 0.5 and Ls is equal to C by Cf equal to 0.95. So, this Ls and Lf consideration, one condition is that when C by Cf is equal to 0.95, then Ls, and Lf when 0.05 C by Cf. So, this is the concept. Similarly, here Tb and this Tb which is provided here, that is equal to C by Cf is equal to 0.05, and here Te equal to when C by Cf equal to 0.95. So, these are some convention it is considered, and at Tb the leading point MTz reaches the end of the bed, when Tb we are considering the MTz end point reaches the Lb. So, this is your breakthrough point. Okay. So, breakthrough concentration is the maximum allowable solute concentration in the effluent fluid. Outlet to inlet solute concentration as a function of time, S shaped curve is called the breakthrough curve, already we have discussed, and prior to Tb the outlet solute concentration is less than some maximum permissible value, say C out by Cf equal to 0.05. So, when we are getting C by Cf is equal to 0.05, there is one condition that up to this we should attain the maximum permissible limit allowable. Like for example, if we use a fluoride solution here, say 6 ppm, but here my allowable limit is 1.5 ppm. So, 1.5 divided by 6, that value should be here when this graph we are considering. So, now at Tb this value is reached and the regeneration is initiated. So, in case of fluoride, say the water present here is equal to say more than 1.5, then it is not acceptable. So, we have to regenerate the bed. If the adsorption is continued at T greater than Tb, the outlet solute concentration should be observed to be rise rapidly, eventually approaching the inlet concentrations as the outlet end of the bed becomes saturated. Time to reach C out by Cf is designated as Te. Now, scale up of adsorption bed for constant pattern formed. So, here say if we want to calculate the length, or if we want to know the LES and LUV, then we can assume that initially the water is going through this bed and the LES gradually increasing, and this front is not like this, it is actually is a S shaped curve. So, this is like this, but in ideal case it would be like this, all the bed is exhausted and this bed is non exhausted, okay, unused, but here this this portion is also unused like this, and this portion is say used. So, this graph is like this. So, with time we will see the one condition is here, that is called Ts, and last condition is Te, and here we are getting Tb. So, this front head two part is not there, only one part. So, this total length we are getting here. So, that is equal to the length of the bed. So, if we divide the total length by this T s, that will be the front head speed. Okay. So, that will be there. So, that concept we will be using to find out the value of LUB. Okay. So, as LB equal to LES plus LUB, and if it is an ideal condition, LUB is equal to 0. Okay. But if it is not ideal conditions, if there is any this mass transfer zone is there, in that case LUB have to calculate. But in all the cases LES can be calculated by this mass balance we have already discussed, that is Cf Qf into T, that what amount of adsorbate is coming through the inlet, that will be captured by this part LES part. So, Qf, that is the specific uptake into mass. So, mass means pi d square by 4 cross sectional area into LES volume into rho b bed density, the bed mass into Qf. So, adsorbate captured by this bed. So, that way we can get the value of LES, and we can calculate the LUB by this formula, ideal wave front velocity into Ts minus Tb, that is equal to Le by Ts into Ts minus Tb. So, ideal front velocity, ideal wave front velocity, that means as we are talking about, say up to Ts is the time, and then the bed, whole bed has been covered by the adsorption process and whole bed is exhausted now. So, we are getting that way the Le by Ts into Ts minus Tb, or Ts can also be calculated by 0 to T 1 minus C by Cf into dt. So, LUB can be calculated that way, LES can be calculated as discussed in the previous slide. So, total LB we can calculate, and if the shape of the experimental breakthrough curve below area B is equal to the curve above area A, like this A and B, if these area are same, in that case we can consider that LUB is equal to half of the MTZ mass transfer zone, and in absence of the experimental breakthrough data, a conservative estimate of MTZ is 4 feet. So, LUB 4 divided by 2, 2 feet. So, 2 feet LUB may be considered as default value. So, then we see that ion exchange phenomena can also be responsible for adsorption process. In apart from that, to get more purified water, we use the ion exchange method. So, as discussed in our previous class on drinking water treatment, then we have seen that for hardness removal the ion exchange can be used. So, here the reagents which are used that are present in RNA2 form, and then calcium, magnesium and other anions present in the solution, and then these cations are attached by this R part and Na is released, and these are the Na salt of these anions are formed, and when we go for the regeneration again NaCl is added because we have to make RNA2. But in case of say cation removal, so this resin is converted to RH2 form, and then these all cations are taken up, not only calcium, magnesium, any other cations, and then it is converted into this, and then the hydrogen hydride form of these anions, and then during regeneration again we use the HCl, so that RH2 form can be regenerated. And when we want to anion removal, then when we want to remove anions, at that time this is formed in R plus OH, and then different anions are removed, and these are R plus these forms, and then during regeneration we add it with NaOH, because again we need to convert R plus OH. So, that this is the regeneration process, and which are followed for the treatment of the wastewater, or to make more pure water, more pure treated water with negligible amount of cations and anions for specific application. And then disinfection in this step, which simultaneously takes or at the last stage of the treatment, tertiary treatment, it is a coupled we can say. So, this disinfection is coupled with any tertiary treatment step. So, here main objective is to remove the pathogens, and then chlorination, ozonations and UV light treatments are normally used, and we have made discussion during drinking water treatment, and same process are also followed in the industrial treatment as well. Up to this in this class, Thank you very much for your patience.